Alright, this is lesson 2.1 of our Pre-Calc 12 class. Unit 2 is called Polynomial Functions. And lesson 1 is called Characteristics of Polynomial Functions. In this lesson, we're going to look at the graphs of polynomial functions, see what they look like. And then we're going to talk about some words we use to describe those polynomial functions. This is the first of two characteristics lessons. We'll cover half of the words in this lesson and half of the words in the next lesson. Alright, so here is our general formula or format for a polynomial function. It is a number x with a a natural number power plus another number x with a power 1 lower plus another number x to the power of 2 lower, and so on, all the way to a constant term. So for example, polynomial function y equals x to the power of 3 plus x to the power of 2 plus x to the power of 1, and then technically x to the power of 0, or just a number. So some examples and non-examples of polynomial functions. A is an example of a polynomial function. It's a number times x to the power of 2 minus 3. B is not, it's a radical function. C is not because we have an x, but its exponent is not just some natural whole number. D is, it's like a polynomial with an x with the power of 1. You could think of it, so this is just a polynomial. E is not a polynomial. A sine function is a trig function. F is not a polynomial function. It's a rational function, as in it's got a fraction. The numerator is a polynomial and the denominator is a polynomial, but altogether it's not a polynomial function. G is a polynomial function. It's written in a factored out form, so it's hard to tell. But if you multiply this out, we get x squared plus x, so that looks more like a polynomial function. We call this standard form. G and H are both in factored form, but if you multiply them out, we get standard form. And then example H, same thing. It's factored form, but when we multiply it out, we see that it's a polynomial function. Okay. Now, the very last term, a sub 0, or like a with a subscript of 0, which is like exponent is a superscript, it goes above, but subscript goes below. So I say a sub 0, and that refers to that symbol right there. A sub 0 is the constant term of a polynomial function. It tells us the y-intercept of the polynomial's graph. That's what it is. So from our examples of polynomials, we have a minus 3 on example A. So a sub 0 would be negative 3. And then we can also say that on the on the graph of this thing, we're going to intercept the y-axis at negative 3. That's all that means. Example B, we have a plus 1. So a sub 0 is 1 from our formula, a sub 0, which makes this the constant term, and it means our y-intercept for this function would be at 1. That one's a little more familiar because this is also a linear equation with a y-intercept of 1. Y equals mx plus b, right? Well, that plus b concept applies to all of the polynomials. Okay, example C, there is no constant term, as in all the terms have an x in them. So we could think of it as a plus 0 for the constant term, which means a sub 0 would be 0, which means we're going to have a y-intercept right at the origin. Example C and D, oh sorry, this is not C, this is a second C. This second example C right here, the two examples on the right, they are both in factored form. So to find our a sub 0, we have to put it into standard form, which means multiply this all out. So if we do that, we can see a sub 0 is 0 for this example on top. And on bottom, when we multiply it out, we see plus 9 for our constant term. So a sub 0 is 9. Okay. Degree. The biggest or the greatest degree, or sorry, the greatest exponent on any of the x's is what we call the degree. So in standard form, it's the n value. So in example A, there's only one x exponent, and it's 2. Technically, the constant term has x to the power 0, but not important. So the degree for example A is 2, because that's the biggest exponent on x. Example B, we just have an x, so we could think of that as x to the power of 1, which means the degree for this polynomial is a degree of 1. Example C is a degree of 3. And our new example E, when you multiply this out, we get an x squared, so we have a degree of 2. And then similarly, we multiply this out, we have a degree of 2. All right, leading term. So once you've identified the degree, the whole term where you found that degree is called the leading term. It's the term with the biggest or the greatest exponent on x. And we include the number in front of x, we include the x, and we include the x exponent. The whole thing is a leading term. So example A, there's 2 terms. X squared is the biggest or greatest exponent, so 5x squared is the leading term here. Example B, x or 1x is a leading term. Example C, a degree is 3, so 4x to the power of 3 is leading term. Examples E and D, we have to multiply out, and we find that x squared is our leading terms. Now leading term is one word. Leading coefficient is a similar but different word. Leading coefficient means just the coefficient on a leading term, or just that number attached to the x on the leading term. So if we know our leading terms, just grab the number. So 5x squared is our leading term, 5 is our leading coefficient. 1x is a leading term for B, so 1 is the leading coefficient. For example C, 4 is the leading coefficient. Examples E and D, 1 is the leading coefficient. Or A sub n is our leading coefficient. Okay, now some other words to describe polynomial functions. The relative extremes, or relative extrema, or just extrema, means all of our local maxes or min values on a graph. Local max is the same thing as relative max or min. So then what is a relative max and what is a relative min? On a graph, a relative maximum value is any hill on our graph. So if we look at this graph, we have at point D seems to be the top of a little hill in this area. So relative to this area, there's a maximum at point D, you could say. So D is a relative max. A relative minimum is kind of the bottom of a valley on a graph. So if I look at B, B seems to be the bottom of a valley in this relative area. So B would be a relative minimum. Similarly, E seems to be the bottom of a valley over here in this area. So E is also a relative minimum. B and E are relative minimums, or local minimums. D is a relative maximum, or a local max. B, D, and E, all three of them together, are relative extremes, or extrema. I'm pretty sure extrema is like Greek or Latin or something, so don't worry about it. Alright, so if I wanted to work with this graph and tease out our understanding a little bit more, let's drill down and exercise the difference between positive and increasing. Positive means above the x-axis, as in the y values are above the x-axis, or the curve is above the x-axis. Increasing means as we go from left to right, our y values are going up. So if we take that out, positive interval is any interval where x is above the x-axis. So on our graph, it's all the green. So from the left up to point A, between point C and point E, and then after point E. Those are all intervals we have where it's positive. The positive intervals where the y values of our function are above the x-axis. Note point E is not above, and it's also not below. So it's neither positive nor negative. It's right at the x-axis, so it's at 0. The y value is 0. 0 is not positive or negative, like that. So when we do our interval notation, we got to exclude E from the t party. And we could do that like this. We use normal brackets on the E in unison with normal brackets, e to infinity. So this says everything below E all the way to C, and everything above E all the way to infinity, but not including E. So if positive intervals are above the x-axis, negative intervals are below. We only have one interval in red here below, from A to C is a negative interval below the x-axis. So A to C is our interval for this section. All right, now increasing. Intervals where the y values are going up. And when we say going up, we mean just like when you're reading a book, left to right. As you move across the curve, starting at the left, going to the right, the y values are going up, it's increasing. If the y values are going down, it's decreasing. So increasing intervals from B to D, as we go from left to right, our y values are going up, 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 up. So we're increasing on this interval. Also, from E to infinity, or E all the way to the right, we are also increasing. So BD in unison with E to infinity. Which means from the left up to point B is a decreasing interval. As we go from left to right, the y value, as we go left to right, the y values are going down from negative infinity up to point B. Also from point D to point E, also decreasing. As we go left to right, y values are going down. So that's increasing versus positive. The point of those exercises on that one is, again, just to make sure we are understanding our graph and kind of building some language around how to describe our polynomial function. This language in particular will be really helpful in calculus when we get to kind of applying our derivative, second big idea. So whether or not you are interested in taking calculus, you will be ready for it. So that'll be great. All right, here's some examples that we didn't do in class. But we have some words to describe polynomial functions. We have some basic familiarity now with the format, the notation. We've identified polynomial functions from other types of functions a little bit. We've talked about degree, leading coefficients, leading terms. We've talked about relative extremes, whether they're maxes or mins. We've talked about positive versus increasing. So in the next lesson, we'll unpack a few more words on polynomial graphs, and then we'll move on.